will not have visionary talk. However, we have very strong visionaries, but also hands-on design executives who come from 2 companies related with the communication domain. We'll be seeing the first one first, that will be presented by Scott Runner. Scott is currently the Vice President of Advanced Methodologies and Low-Power Design at Qualcomm. He has worked in engineering, in semiconductor, in EDA industries for over 30 years, holding positions in IP, in design automation, management at Connexent. Also, he's a founding member of the Designware team of Synopsys. He's worked in DSP, in ASIC design engineering, and he has been the center manager, design center manager at Fujitsu Microelectronics. Scott has taped out over 48 devices. So we're very excited to hear about the most recent experiences of Scott. Scott holds a bachelor degree in physics with emphasis in computer science and electrical engineering from Georgia Tech. Scott, please join me in welcoming Scott.
Good morning. So today I'm here to talk to you about some of the problems and some of the solutions in designing the SoC mobile processor, a key technology in enabling what has become the largest technology platform in history, the smartphone. Now, if we look at the smartphone today, we see that its genesis was as a voice phone. There are over 6 billion voice connections and mobile connections today. 1 billion people access social media with their smartphones today. 80% of smartphone users use their phone as their primary camera. Almost 80% of them use their device for navigation. And nearly 70% of them use the phone as their primary music player. So this device truly has become an integrated platform for a variety of disparate technologies, or seemingly disparate technologies, that have now come together to provide one user experience. Now, we also have a number of emerging technologies that start to combine, again, a number of seemingly disparate technologies. For example, augmented reality, wherein we take computer-generated graphics, audio, and smart text and superimpose that with a real-time rendering of the environment, video, audio, etc. We also have contextual awareness, wherein we take a user's learned preferences, combine those with global positioning, geofencing, in which I have a spatial proximity of what's around me, image recognition, and environmental and motion sensors, and combine these things together to provide unique applications that we've never thought of before. For example, it'll help you take your shopping list and find the most efficient route in which to shop and the least costly route in which to shop, or can help you play around with learning more about Star Trek Into the Darkness. Now, what's required to enable such a device? Well, we have a variety of different technologies that are required to be pulled together and integrated into a small form factor in order to facilitate this. So we have at the heart of this the mobile SoC processor that must be married together with a power management integrated circuits, with RF, with sensors, both environmental sensors and mobility sensors, display, battery, etc., into a small form factor that has to be light and low cost. That's not a challenging design, is it? So if we see, we have a number of these different technologies, and each of these technologies is growing in their own technology roadmap to provide more and more capabilities. So how do we pull off the design of such an integrated platform? Here's an example of a Qualcomm Snapdragon 600 mobile processor. And then recently we announced our Companion 800 mobile processor. So this device incorporates a quad-core CPU that's running at 1.9 gigahertz. It has 3 levels of caching, as indicated here, but the CPU accounts for less than 15% of the total die area. The other components that are incorporated here include the GPU, DSPs, a modem core subsystem in concert with the DSP, memory, because we obviously have to be able to deliver sufficient bandwidth for this to be able to support these concurrent operations. So this supports 32 dual-channel LPDDR. We also have a GPU that provides execution speeds on the order of a PS3 kind of platform. Video, which supports up to 1080p HD display and Dolby Digital Plus decode. And the video supports both decode and encode operations. The camera supports a resolution up to 21 megapixels and stereoscopic 3D using multiple cameras. And the display supports 24-bit QXGA as well as supporting 1080p through an HDMI external interface. The device supports wired connectivity through USB, PAN connectivity through 802.11n and AC, as well as Bluetooth and FM wireless connectivity. It also supports GPS for positioning for automotive, for pedestrian, as well as to support indoor location-based capabilities with high resolution. And it's implemented in a 28-nanometer LP process. I should also say that that device is a multiple air standard device supporting 3G, 4G modem technologies with a variety of handoff configurations, and we'll go through that in more detail later. Now, what are 3 of the challenges I'm going to talk to you about today? And there's a myriad of challenges in developing a device like that, but the 3 I'm going to focus on are the power challenges, verification and validation challenges, and hardware-software co-design challenges. Okay, first, regarding low power. Well, first, you saw is the myriad of applications that are converging together. Well, those applications, in order to enable more and more growth of those kinds of applications, the underlying technology engines have to grow in performance as well. So what we see here is a plot of the relative performance increase of GPU, CPU, and memory bandwidth over time, paired against the power savings that one is getting from process shrink. So what immediately jumps out at you is process scaling is insufficient to be able to support, insufficient alone and of itself, to support the increase in performance that is required to enable all these exciting new applications. Further, we see that there's a tremendous amount of feature growth. So you saw that device, which integrated all those different functionality. Compare that with a device 5 years ago in terms of the feature set, and you'll see a distinct difference in growth of features. And there's new and more features that are being added. Well, features means transistors. And not only logic transistors, but also memory as well, because software is growing faster than the hardware. And the memory required to support that software is growing at a very rapid clip. So the fact that I've got such radical performance increases on these SoC mobile processors in conjunction with the feature growth, that in of itself is challenging enough. But add to the fact that we have significant limits. First of all, the smartphone itself, its form factor and packaging constraints today, and it married with its cost constraints, puts us in a thermal envelope or a thermal limitation of about 4 to 5 watts. Compare that with a laptop, which is over 20 watts. And you can see that the laptop obviously has a lot more latitude to burn power. But add also to that the growth in battery technology is not keeping up with the increased demand to power consumption of the mobile platforms. So we see, for example, that a smartphone has around 1,000 milliamp hour battery capacity, give or take a lot of different models, whereas a laptop has about an order of magnitude more capacity from a battery perspective. So now I've got these increasing performance requirements, I have these increasing performance requirements, I have the increasing feature growth, and yet I'm constrained in terms of the limits from a thermal and battery perspective. Now, we talked about the growth in terms of GPU, CPU, memory bandwidth and capability. Well, what about COM itself? So here's a plot of over the last 10 years, in fact, less than 10 years, you see more than a 10x growth in bandwidth with the emergence of 4G and a variety of different 4G standards and moving up into carrier aggregation, where we're now starting to combine a number of different carriers and a number of different sources to be able to achieve this high level of bandwidth that's required. So again, just as a summary, we have an exponential increase in performance, a radical increase in feature growth that tracks along with Moore's law, and yet we have to fit that within thermal and battery capacity limits. Now, another aspect of this is we talked about all these disparate and concurrent types of applications that we're running. So it used to be the case that you'd be on a voice call and you'd be talking and you wouldn't be able to check mail, right? Well, we've come a long way since then, right? Not only can you be on a video call at the same time, you can be on a video call playing a game and sharing that with your friends. And you can be on a video call sharing multiple images and multiple streams of video. So we're going to see more and more and more of this. The concurrency is on the rise. Well, what does concurrency lend itself to? Well, if we take a look, in the past in a laptop setting, I might have seen, for example, the CPU and the GPU being the most active consumers of power, and they have certain power profiles related to the application load that's placed on them. Add to the fact, however, now that you've got, for example, an LTE voice call that might be running at a Cat 3 or a Cat 4 rate. On top of that, I've got video encode and decode that's going on. I have graphics that's going on in the background as well, and a variety of other lower power consumption types of functions. So the superimposition of all of these gives you an overall power profile that you have to manage. And again, it has to fit within that thermal profile, both in terms of steady state as well as transient behavior. And it has to fit within the battery limits and the power management limits, both, again, from a steady state as well as a transient perspective. So that provides another set of challenges for us to be able to solve. Okay, so how do we solve these? Well, first and foremost, realize that this is a system design problem. It's not just a VLSI problem. It's not just a processing problem. It's a system design problem. So what we look at is we need to address system architecture, workload partitioning, hardware-software partitioning, how we model these different power requirements and power characteristics and explore different architectural trade-offs, and how that gets mapped into what we do at the VLSI level in terms, and the RTL level in terms of transistor level design, circuit design, and microarchitecture, at the system architecture level in terms of busing, memory bandwidth, et cetera, memory architecture, and hardware versus software acceleration. Mobile software partitioning in terms of how we optimize the overall software, how we leverage the OS, and what kind of tools and APIs we need to facilitate that. So that's, first and foremost, it's a system design problem. Then we need to obviously design each of the IPs that are being integrated, the CPU, the GPU, DSP, memory, et cetera, to be optimized for the mobile platform. Not just a general technology that could be used for, a server or a desktop or a laptop and also applied to a mobile platform, but something that's specifically targeted to this problem set because it's so unique and so demanding. And also, of course, then we must marry that with effective power solutions. So there's a plethora of power technologies available to us, but the question is, which of those technologies provides the best return on investment given all the other constraints that I have? A professor of mine early in my career said, the difference between engineering and science is that engineering is science with constraints. Well, here I think we have a number of different constraints that say, I've got a lot of power technologies, but which ones can I integrate given the cost budget that I have? Which ones can I integrate given the time to market demands that I have and the reliability requirements that I have? So there are definitely a number of power technologies that we can use in terms of dynamic CPU, GPU control, obviously dynamic voltage and clock scaling. We can use a number of different power partitioning, power gating techniques. There's a number of different techniques. The list goes on and on. The key is picking the ones that provide the best return on investment. So the chart down here at the bottom kind of shows what we're dealing with at the end of the day, too, in terms of being smart. This basically shows that if I'm executing a high-performance load on a given mobile application, how long can I run that given my thermal and battery limits, and this one's thermally constrained. So you get the idea again that I have to be more intelligent in terms of what I'm doing and when, but if you recall back to the earlier slide, I've got all those different disparate power profiles. How do I know which ones I can do at any given time? So it takes a lot of intelligence in the hardware-software solution. So that's the overall power problem. Now, what about verification and validation? So it goes without saying that, that register growth implies exponential state space growth. We've all become aware of that. But what does that mean? Well, it means obviously a permutation in terms of the number of units, the size of units, the number of interfaces between these units. And those units are very disparate. You know, if you tend to look at, for example, certain network processor chips, I may have ingress ports and egress ports, and I've got deep packet processing, a lot of stuff going on, very complex devices. They're fairly regular types of structures. If you look at an SoC mobile processor, it's extremely heterogeneous. So if I look in one area of the die, I've got modem processing, I've got video and audio processing, I have graphics processing, then I have a CPU processor, memory bus, et cetera. I have mixed signal components. I have memory components. I need to interface through, say, a stacked die configuration to memory. And I have a lot of options in terms of how I do these things. So the challenge from a verification point of view is significant, both from the complexity growth perspective as well as the heterogeneity of these kinds of combinations of complex things. The other thing is, it's not just a verification problem and a traditional validation problem, but, and I'm going to jump down here, but it's also how do I validate these complex scenarios and system-level scenarios and do all the testing that's required for a smartphone application. So not only do I have to go through traditional silicon validation, I certainly have to pay attention to performance, security, power validation. I have to address regulatory and conformance testing or type approval. I have to address interoperability and field testing, compliance and qualification testing, user interface testing, et cetera. It is a system on a chip, and it requires all of these different types of testing strategies to address it. But compounding that is the fact that defects are not limited to hard functional failures, and as we move down into deeper and deeper submicron geometries, we're seeing that process variability is becoming a more and more significant factor, both from a timing point of view, from a power point of view, and an overall reliability point of view. Further, you know, there's the notion of, you know, is there such a thing as zero defects anymore? And I remember early in my career, having worked at Fujitsu, the requirement was I had to tape out a device and it better not have any defects. And that was a long time ago. So, and if there were any defects, you had to stand up in front of upper management and kind of fall on a proverbial sword, and you were in a lot of trouble. But today, it's very difficult to achieve zero defects. And even what is a defect is becoming a little bit more gray because of the variability issues. So one of the challenges is, well, how do I verify with the goal of being to achieve what is good enough? And what is good enough means, at the end of the day, what works for a customer. So marrying both verification and validation together. Okay, so these are some of the challenges related to the overall verification and validation approach. So let me kind of illuminate that with an example. So here's a case where I've got evolution data, a number of different modem air standards. So I've got evolution data only. I have GSM GPRS. I have CDMA1X, UMTS. I have time division synchronous CDMA. I have then LTE, both time division and frequency division duplex air standards, okay? Now, in a typical phone today, I don't have just one of these. In Qualcomm phones, you have all of these, because if you're in different market segments in a world phone, you have to be able to hand off between them. Well, how do I possibly verify that? Because if you take a look at the number of permutations of handoff combinations, not only do I have to address system selection and redirection, but I also have to address the handoffs both under a normal condition, a fallback condition, and a number of other exception and error conditions between different protocols while you're moving, going through different environments, and I have to be able to do that across different frequency bands. Oh, and let me add to the fact that in addition to wireless WAN, I also have to deal with the wireless WAN and wireless PAN connectivity that's going on as well. So I have a lot of RF going on, and I have a lot of communications protocols that I have to be able to verify the handoff of in order to ensure that the system is reliable. So, for example, in San Diego and other places, you'll see Qualcomm vans driving around with phones under test to be able to validate some of the assumptions with a lot of these different handoff techniques. Okay, so what are some of the solutions that where we could approach this particular problem? Well, certainly one would be verifying at the system level. Again, we're dealing with a system level problem, therefore I need to attack verification and validation from a system level point of view. So that means obviously higher abstraction. How do I have those higher abstractions that I can use to validate the overall architecture? How can I reuse verification and validation throughout the flow? This is a discussion that I've had with a number of people, is that you notice this type of device and it requires a significant amount of domain expertise. I have to have modem experts, graphics experts, video, audio experts, CPU experts, bus experts, RF experts, power experts, security experts. I mean, that is a lot of domain knowledge. So one of the tricks would be, how do I reuse such domain knowledge throughout the flow with that, because it's not possible that the entire organization can have all those areas of expertise. The other aspect is what I'm terming multi-dimensional verification and validation. So I can't go off and just verify power and separately verify security and separately verify mission mode functionality of, for example, graphic rendering. There's a combination of those things, the intersection of those things. So how do I effectively address these different types of verification strategies that need to be crossed with each other? And that's kind of what this simple diagram is intended to illustrate. And then last is the key of, well, how do I enable that? Well, I need, obviously, a focus on methodology and methodology innovation. It's very critical to be able to support something like this. Brute force approaches are running out of steam. Abstraction, reuse, and automation are obviously inherent. Formal verification techniques, in addition, as a complement to dynamic verification techniques. And then a variety of engines. Faster simulation, simulation acceleration, emulation. Do I need just one of them? No, we need all of them, because if you notice the different types of verification activities we're executing, they have different performance requirements and different timeline requirements throughout a design flow. Okay, then the last item is regarding hardware software. Okay, so first of all, and I think this is a pretty popular picture from IBS 2009, which showed the overall design cost broken down as software compared with other hardware activities, including verification, architecture, physical design. And I think we see the same thing, that software is definitely growing at a faster clip than hardware is. And I think in many organizations, you'll see that the number of software engineers is starting to eclipse the number of hardware engineers. The one challenge here is that as hardware grows, it has its exponential state space explosion. But add on top of that, software has its state space explosion. And then the interfaces between the two obviously get commensurately more complicated. Add to that the fact that we have multi-core designs that are increasing at a very rapid clip. And by the way, when I use terms like heterogeneous core, don't read big little into that. It just means heterogeneous. Okay? They're different. I might have a hardware acceleration engine. I might have a different class of CPU in one area, GPU in another area, et cetera. But now I have to deal with that software integration problem on hardware that deals with a heterogeneous set of different cores. And then what about the real-time requirements of those particular platforms? So I have some functions that must be done in a given amount of time. I have other functions that have more tolerance in terms of the amount of time that they get executed in. So when I've got a very complex system that's executing all these things concurrently, how do I manage those different types of temporal constraints? So, how has software tended to be designed, historically? Well, you take a system spec, you get a hardware spec, and then we have the hardware design process, and that renders a device. And then independently, we kind of have the software design aspect, and there's some kind of loose interaction along the way, and then software gets integrated onto the device. Well, when you're trying to address such complexity in a very short period of time, it's difficult to do this. So, of course, in terms of positing some possible solutions here, I think hardware-software co-design and co-verification has certainly been academically and even talked about in industry for a couple of decades now. And it's as philosophical and religious as you could possibly get, I presume. But I think one of the issues is that some of the solutions may not be anchored purely in technology. So I look here and I say, do we expect hardware and software to use exactly the same tools? Do we expect them to have exactly the same design timelines? Do we expect to have just one model and that abstraction is going to suffice for both hardware and software design? I don't really see that. What I see is, first of all, a collaboration between the hardware and the software teams in terms of documentation and specifications, and in terms of overall collaborative platforms. So these things ideally are executable, but in whatever form they are, the key is the word collaborative. So I think, certainly there's a demand on platforms to say I need model-based platforms, and I need simulation acceleration platforms, and I need emulation platforms to be able to foster this type of environment. And then what about the issue of designing hardware for software and software for hardware? Meaning that, again, back to the earlier picture, if these two are completely independent, did I really design my hardware to be software friendly and my software to be hardware friendly? So to do that requires some system level analysis, building in appropriate debug solutions, designing interfaces to be able to support this type of hardware, software. And then consider, though, the fact that I've got domain-specific solutions. I have multiple stacks for different types of functionality that's integrated onto one particular given device. And last, how do I address that with multiple concurrent types of use cases? So I think the key is figuring out, obviously, how these teams can work together without over-constraining the problem. Okay, so I've talked to you today about 3 sets of problems in designing an SoC mobile processor for smartphone applications. We talked about low power, we talked about verification and validation, and we talked about hardware, software. I think you see that one of the key messages was it's a system-level problem, and it takes system-level expertise to solve that. The other thing I think you'll see is that if I've got 1,000x bandwidth improvement over the next less than 10 years, I've got all these features per phone and all these numbers of phones, what kind of infrastructure do I need in order to be able to address this? And our next speaker, I think, does an excellent job at addressing that. All right, thank you. You're back.